Swayam Prabha. Digital India. Educated India.
Good morning friends, we are back with the fourth lecture for week number 3 where we are talking about the application of digital techniques in mechanical measurement. In fact, I am telling good morning because I am recording this video in a very cold and wet morning at Guwahati, but you may be seeing this one at some other time, so please alter the initial introduction that way. Now, in the earlier 3 lectures we have mostly covered all the relevant topics apart from only one which is left for today's discussion. We have discussed about the number system, we have discussed about the importance of digital transmission over analog transmission, we have discussed about why binary is generally preferred over other number systems like decimal, octal or hexadecimal. And then we have seen the use of logic gates and their combinations to transmit the data or to modify the binary data. And in the last lecture where we have discussed about different methods of converting an analog signal to its digital counterpart. Today we shall be discussing the other version or the other extreme of that, that is converting the digital signal to its analog counterpart. But before that, like we always keep on doing, let us do a little bit of exercise based upon what we have already discussed in the previous lecture. So, in the previous lecture we have discussed about converting an analog signal to digital signal using different kinds of devices. We have talked about the digital ramp ADC, the integration based ADC, single slope or double slope, successive approximation ADC, sigma delta ADC and also the flash ADC, each of them having their own advantages and disadvantages. Let us take one example of an analog signal and see how we can convert this to a digital signal or what will be the corresponding digital signal. One thing you must keep in mind, it does not matter what kind of conversion system or what kind of ADCs you are using, as long as the resolution of the instrument is same, the analog output should also, the digital output corresponding to the analog input should also be the same. Let us say we are dealing with a device which is having a voltage range of 0 to 10 volt and it is a 4-bit device. That means whatever analog input you provide within this range of 0 to 10 volt, that will be represented by a 4-bit binary number. That is a binary number which can comprise of 4 digits. This is the way we represent the bits, where the first one corresponds to the least significant bit or 2 to the power 0, then this is 2 to the power 1, this corresponds to 2 square, this corresponds to 2 cube. Here this one is the least significant bit, this one is the most significant bit. So, it does not matter, I repeat, what kind of device you are using, but you should get the same binary output. Then let us say the input that we are providing is 3.187 volt. Somewhat randomly I have chosen a value, then what should be the digital counterpart corresponding to this, that we have to identify. So, first can you decide what is the resolution of your converter? If range is 0 to 10 volt, that is maximum voltage can be 10, minimum voltage is 0 and it is 4 bit. 4 bit means how many total number of levels it can have? It can have 2 to the power 4, that is total 16 level, that is starting from 0 to 15. These are the different levels it can have, and we have to identify this input value of 3.187 falls in which one, then accordingly we can get its digital counterpart. Now the resolution of this one, Q should be the maximum voltage minus minimum voltage divided by 2 to the power 4, that is 10 divided by 16, which is 0.625 volt. So, width of each such level should be 0.625 volt, and then we have to identify exactly where it should fall. There are we can identify it in say very crude way, or we can go in more systematic pattern. Crude way means, let us say the first level corresponding to level 0, what should be the voltage corresponding to this? It should be 0 to 0.625 volt. Then level 1 corresponds to 0.625 to the double of this one, that is 1.25 volt. Level 2 should be 1.25 to 1.875 volt. Then level 3, it should be 1.875 to 2.5 volt. Level 4, it should be 2.5 to 3.125 volt. Note, each of them is having a width of 0.625 volt. So, according starting from 0, we just have to keep on adding this 0.625, and we can identify the starting and finishing point of each of these levels. Now, come to level 5, it is starting from 3.125 and it is going up to 3.75 volt, and our objective is 3.187, which falls right here. That means, it should belong to the level number 5. Then we can identify the binary value corresponding to this 5 digital value or decimal value, and that should be a binary output. So, what is the binary correspondence to 5? 5 divided by 2, you are getting 2, left 1, then divide 2 by this, you are left with 1, remainder is 0, then divide 1 by 2, you are getting 0, left with 1, and to get the 4-bit representation add another 0. So, this should be the binary value, that means you should get 0 1 0 1 as the output for this. However, this is a very crude way of calculating. If we think about any particular kind of converter, any particular kind of DAC, then how can we achieve this? The one that we have done here, that is somehow or somewhat that is the way the digital ramp one goes off. That is, it keeps on changing the binary value by a free running binary counter, and then it keeps and compares the corresponding output voltage with the actual input, and then gives a finally settles to a particular value. Like if this conversion we are getting using a dynamic ramp converter, then it should be starting from 0 0 0 0, and whatever is the corresponding voltage, it will compare with this. It is not matching, this is smaller, so it will change the least significant bit. It is still not matching, then it will go to the next one, which is this, then the next one, which basically it is our level number 0, this is our level number 1, this is level number 2, this is level number 3. Whenever it is getting one binary number from its register, it is converting this digital value to the analog value and comparing that analog value to the actual input, which is this one. As long as this the output from the digital to analog converted value is less than the actual input, it will keep on changing. So, next value should be 0 1 0 0, which corresponds to level number 4. It is still not matching, then it changes this, reaches level number 5, and now it gets a value. Basically, the value corresponding to this one will be coming to be within the range of this 3.187 volt, or rather I should say the 3.187 volt will come within this range, and so it will settle this to this value. This is how a dynamic ramp one goes on. Whereas, if we think about a successive approximation DAC or ADC, successive approximation ADC, then how it works? It starts from the most significant bit, whereas here we are starting from the least significant bit, here we shall be starting from the most significant bit. So, the most significant bit will be set as 1, others will be set as 0, or let me do this way. Let us say this is your register, this is the most significant bit, this is the least significant bit. Sometimes this is called the second significant bit, this is called the third significant bit, but not that much important these terms. The MSB and LSB are more important. So, initially all of them are set to 0. Now, when the conversion process starts, the register will convert the value of MSB to 1 or set it to 1. Then 1 triple naught. Corresponding to 1 triple naught, what should be the value? The corresponding value is 5 volt. Now, this is greater than this 3.187. So, this is not possible. So, this goes back to 0. The MSB is settled. Now, it changes this second one to 1. What is the corresponding output value? Corresponding output value should be, you know the resolution. So, corresponding value should be 2.5 volt. I hope you know how to calculate the voltage corresponding to this. Now, this 2.5 volt is coming to be less than 3.187. That means, this is a correct one. So, we settle this one, this is settled. Now, we move to the third one and the register set this to 1. Now, what should be your output value? Your output is, now for the first significant bit it is 0 into 5 volt, or rather the most significant bit, plus now the second one is finalized to 1. So, into 2.5 plus the 1 in the third which we have just set into 1.25 plus the last one 0.625. So, we are getting this to be 2.5 plus 1.25, that is 3.75, and this 3.75 is found to be greater than 3.187. So, this is also not correct. So, this goes off and the register sets this one back to 0. This is also final. So, we have already got 3 digits or 3 bits. Now, go to the least significant one, set this to 1. Then what is the value corresponding to this? The output voltage, like corresponding to this binary representation, corresponding digital to analog converter will give you 0 into 5 volt plus 1 into 2.5 volt plus 0 into 1.25 volt and finally 1 into 0.625 volt, which should be 3.125. 2.5 plus 0.625 is 3.125, and this is coming to be less than 3.187. So, it will continue with this value, giving a final output as 0101, which is essentially the same as this one. So, this is the way a digital RAM converter works. This is the way a successive approximation converter works, and they should give the same value. However, instead of having the same resolution, if one of them is having say this 4 bit resolution and this one is having a 3 bit resolution, definitely corresponding outputs may be different, because here it will be using 4 binary digits, whereas this one will be using 3 binary digits. But if the resolution is same, the voltage ranges are same, or I should say the number of bits and voltage ranges are same, then corresponding binary output has to be exactly the same. Now, let us move to the topic of our discussion for the day, which is digital to analog conversion. In digital to analog conversion, we have a binary input which gets converted to an analog signal output, generally in the form of a voltage. So, the application of such device is probably more than the analog to digital converter, because in most of the cases when you want to store some analog signal, we convert that to digital cases and we store it or transmit it for the corresponding advantages. However, quite often we want the final representation, final output in analog form itself. Therefore, whatever binary data we have stored or we have processed or we have analyzed, that needs to be converted back to the analog form, and then we can get the final output from this. Just think about one application, a very common application of a telephone receiver. When we are talking, like here, the sound wave that is coming out, this sound wave gets converted in the microphone to an analog form, or sorry, this analog sound wave or analog signal gets, the sound signal gets converted to a digital form, and this digital form that gets transmitted through the wires or through whatever means, like in case of mobile phones they get transmitted via wireless connections, and they goes back to the, or they goes to the destination where they are supposed to reach. Now, there in the handset the digital signal gets converted back to analog, and we get the sound wave back, the analog sound wave, and so the recipient is able to hear the sound. Basically, the telephone receivers or the mobile phone receivers that we have, they are they can do the both, means they can convert the sound wave to the digital form, thereby facilitating the analog to digital conversion, and similarly when we are receiving a call or when we are, rather I should say, when you are hearing the sound of the person other end of the phone, then it is converting the digital signal to the analog sound wave, so that we can hear what they are saying. This way there are several kind of applications, probably infinite number of applications of digital to analog conversion. So, the digital to analog converters or the DACs, their primary objective is to convert a binary number into voltage proportional to its value. The voltage will be the voltage we can use some suitable calibration to get the actual output that we are looking for. So, each of the binary digits should have a corresponding voltage value associated with this. Like say if we are talking about a binary representation with these digits like shown here, then the first one, if that is representing 0, then whatever distance we have between the first and the second one, similarly the same distance we should have between the next two, and again the same distance we should have between the next two. So, this way each of them gives a finite value of the voltage, and the objective or the entire working procedure of this DAC is based upon assigning the suitable voltage or give the suitable voltage output corresponding to whatever binary number that you are giving. There are several properties of importance to DAC, but most of you are already known to you. Firstly, from our discussion of the first chapter, first module, where we have learned about different properties of measurement systems, and also in this week itself when we have discussed about different terms associated with the analog to digital conversion, more or less similar properties are also relevant to DACs. First is definitely resolution. Resolution refers to the smallest analog increment corresponding to 1 bit change in the digital input. Like if there is a small 1 bit change, generally in the least significant bit position, whatever change in the final output that we get, that is what we refer as resolution. And quite similar to the analog to digital converters, here also it is set to be the voltage associated to the V of the least significant bit, or you can say the reference voltage divided by 2 to the power n, where n refers to the number of bit. Like if the reference voltage is set to be 10 volt and you are talking about a 4 bit converter, then it will be 10 volt by 2 to the power 4, that is 0.625 volt. Just the same way we calculate for ADCs. So, it is always desirable to have higher resolution. Like any measurement device, we always want higher resolution. That means with the smallest possible change in the input, we want larger change in the output. That is what the basic definition of resolution is, and the same is applicable here also. When you have larger resolution, we always prefer to go for that device. Like just see this example. Here our analog desirable analog signal is something like a parabolic curve. This is the desirable analog signal or analog output which we are looking for. But as we are using a 1 bit converter, then it can have only two levels, 0 and 1, because it is a 1 bit converter. So, it can have maximum 2 to the power 1, that is 2 levels which are 0 and 1, and therefore, it is giving a representation just like this, either 0 at one position or 1 at the other position, and all values are represented either by this. Whereas, the same thing if we represent by a 3 bit converter, 3 bit means we can have 2 to the power 3, that is total 8 number of levels starting from 0 to 7, or if we write in binary format, we can have 0 0 0 to up to 1 1 1, and so many levels we have available with us. Accordingly, it can give a much better representation just like this. So, 0 0 0 is the lowest position, 1 1 1 is the highest position, and in between we are still having 6 more levels. So, it is a much better representation that we are going to get. So, it is always better to go for a high resolution converter, but there are practical problems as well. Then the reference voltage. The reference voltage which we have already used for calculating the resolution, it itself is a term of importance, because it is a specified voltage which determines the magnitude of the resolution itself. It determines how much voltage we are going to assign to each digital level. So, higher the value of V reference, definitely higher will be the resolution. And reference voltage can be of two types. One can be the non-multiplier type, which are internal to the device, set by the manufacturer itself and user is not able to change it. Other is the multiplier type, where the user can set the reference voltage by using some external voltage source, and therefore, it can be made to be variable, which is not possible in non-multiplier type. Another property of importance is the settling time. Settling time refers to the time required by the converter to settle within a specified band around the actual output, and this band, width of the band generally is equal to the resolution itself, and therefore, the band can be specified something like plus minus q by 2, just like this. Here this line represents the expected output. However, depending on the way your converter is working, we are getting a curvilinear representation where initially there is a large overshoot and then that gradually decreases to get settled within this band. So, we can allow a maximum of plus minus q by 2 amount of error, and once this term gets settled, like if you look, say this is the point, beyond after that the value, output value is always within that plus minus q by 2 range, and so this is what we refer to as the settling time. So, to note the reading or output value from your converter, we must be aware about the settling time, because that is the minimum amount of time we have to provide to our instrument before finalizing or before noting the final reading. Next property of importance is the linearity. Like any measuring instrument, we always expect a linear behavior, that is with the whatever change in the input is taking place, proportionate amount of change in the output should also take place. So, linearity refers to the difference between the desired analog output and the expected output over the full range. Like, see, this is the case, this is the most ideal scenario, as the input is changing continuously or corresponding output is also changing, and the midpoints of all these intervals can be joined by a straight line. This is the desirable scenario, but this is what we may get in practice. Like there can be some quite random variation, non-linear representation of this output. This can lead to severe amount of error in the final reading. And the speed or conversion rate is always of importance, which refers to the rate at which the digital input gets converted to the analog output. It depends on the clock of the input signal itself and also the settling time. Like larger the settling time, definitely it will be able to give you reading within a lesser period of time, but again that affects the accuracy. So, each of them needs to be considered while designing a DAC, and still we can have several kinds of errors, like we can have error associated to the gain of the instrument. Gain refers to like the gain error refers to the change in the ratio of output to input with time, whereas offset refers to if there is a fixed amount of distance maintained between the expected output and the actual output over a long period of time. When this gain and offset comes together, then we get the full scale. I am not going into the detail of this, because these terms already you know. In the very first week itself we have discussed about these kinds of errors. The gain error or corresponding slope related error we have discussed in detail. We know how to calculate that for a general instrument also. It is just the same thing, but it is digital to analog conversion version. That resolution, we have already seen how resolution can give erroneous results. Non-linearity, the example again we can see here itself, the example of non-linearity error. Non-monotonic is somewhat similar to this non-linearity, and overshoot, this is what we refer to as the overshoot, because this is your desired level, but over this entire span the output is greater than the actual input or actual expected output, I should say. So, this is what we refer as the overshoot. So, large overshoot can severely hamper the working principle of the instrument and even cause permanent damage to that one also. So, these are certain properties which are of interest related to the digital to analog conversion. There are quite a few kinds of such converters, but here we shall be discussing only two of them, which are the most popular one and also the most important ones. The first one is called the binary weighted register. In case of a binary weighted register, we have a series of registers each connected to one bit of the binary input. That means, if there are you are having n number of binary, if your instrument is of n bits, then we are also going to have n number of registers, but these registers are not equal, rather they follow a particular pattern. Like the register connected to the most significant bit, if the value of that one is R, then the one connected to the next one, its value will be double of that is 2 R, the next one will be having a value of 4 R, and this way it will keep on going. So, we have a network of n number of switches. These switches are controlled by the binary input of the corresponding bit. Like say for the most significant bit, when your most significant bit is equal to 1, then this switch is closed, or this switch connects this particular portion. So, it is in contact with the voltage source. However, when your most significant bit goes to 0, then the switch contacts this grounded portion. So, no current flow through this. Then the weighted resistor of ladder network that we have here, every resistance is inversely proportional to the numerical significance of corresponding binary digit, just what I mentioned. Like for the most significant bit it is R, then it keeps on becoming double of the immediately neighboring one as we keep on going across the bits. Then what will be the resistor corresponding to the least significant bit? Then the first one is R, the next one, first one which is associated with Bn position is R, then the one associated with Bn minus 1 position is 2 R. So, we can write this to be 2 to the power 0 R, this to be 2 to the power 1 R, then the one associated with Bn minus 2 position is 2 square R. So, this way if you keep on going, the one associated with B1 position, what should be the value of this? Let us see quickly. It should be 2 to the power n minus 2 into R if we keep on following this pattern, because instead of writing this to be 2 to the power 0, we can write this to be 2 to the power n minus n. Similarly, we can write this to be 2 to the power n minus 1, and the same we are writing for all of them, and the final one. So, this way you can keep on writing the resistors for all of them. This is what we have here. So, the total current that will be flowing through this entire circuit should depend on the reference voltage divided by corresponding R and the value of the switches. This B values refers to the value of the bit. If the bit is 1, then this you will be getting current as V ref by R, whereas if B is 0, there will be no current flowing through this, and same for each of the resistors. So, we sum them up starting from Bn minus 1 going to B naught. Actually, I made a mistake while writing this. So, the most significant bit we refer as Bn minus 1, corresponding resistor is R, or 2 to the power 0 R. Then we can write this to be 2 to the power n minus 1 plus 1, something like this, or rather minus 1 just to make it 0. Then the one in the next bit 2 to the power Bn minus 2, its value is 2 to the power 1 R. Then we can write this to be 2 to the power n minus its position n minus 2 R minus 1. So, the one in the ith position, then what we should write? The corresponding resistor should be 2 to the power n minus I minus 1 into R. This should be the corresponding resistor. This is exactly what we have written here, and each of them is having corresponding resistance. The magnitude of resistance keeps on changing as we move from most significant bit to the least significant bit. The one connected to the least significant bit is the highest resistor. Then this is the total current. Then how much will be the voltage at the output? This should be this current multiplied with this RF. So, it is I into RF, and we have the expression for this. Let us so the full scale output current will be possible when your all the bits are having 1. Like if you are dealing with a 4-bit resistor, or rather 4-bit converter, then if all of them are 1, then you will be going to get the maximum current, which we refer as the full scale. Similarly, when all are 0, then no current will be flowing through this, output voltage also will be equal to 0. Let us take the example of this particular resistor. In this particular resistor, we are dealing with a 4-bit converter. So, 4-bit means first one is having resistor R, second one is having 2 R, or you can say 2 to the power 1 R, then next one is 2 square R, and third one is 2 cube R, which is connected to the least significant bit. This one V ref amount of voltage has been applied, and RF, this resistor is taken to be equal to R. Then what is the current that is flowing through this? It is very easy, you can calculate to be V ref by R into B3, as we have taken R outside. So, B3 plus B2 upon 2 plus B1 upon R, B1 upon 4 plus B0 upon 8, where B0 refers to the least significant bit, B3 refers to the most significant bit, and then output voltage will be RF times of this, and as RF is equal to R, we get this. So, therefore, say we are dealing with a situation where your binary input is 1011, then how much will be your output voltage? Your output voltage will be equal to V ref into RF upon R into 1 corresponding to B3 plus 0 corresponding to B2 plus 1 corresponding to B1 plus 1 corresponding to B0, that is V ref into RF upon R, and then if we add all of them together, we have 8 plus 2 plus 1, that is 11 by 8 V ref into RF upon R. So, this now by changing the value of this V ref, RF and R, or I should say the ratio of this RF upon R and also the magnitude of V ref, we can get any desired level of this V out. This situation where RF is equal to R by 2, we get this value. So, by just modifying the value of RF by R ratio and the value of this reference voltage, we can produce any level of output voltage corresponding to a given digital one. So, the biggest advantage of this structure is it is a very simple, easy to understand structure. It is an economical construction from design point of view and also easy to analyze, and quite fast conversion, because as all of them are working parallelly. So, it is very fast. But it involves a large number of registers, particularly when we are dealing with a higher bit one, then quite difficult to maintain the precision and accuracy level and also the stability of the lower registers. Like suppose if you are dealing with a 16-bit converter, then if the one associated with the most significant bit is R, the one associated with the least significant bit is 2 to the power 15 times of this R, which is an humongous value. Even if your R is small, this one is an extremely large register that you are talking about. So, it is becomes quite difficult to handle with them. Another problem happens, actually all these problems are associated with the presence of so many number of registers. Now, if you are doing or dealing with an application which is associated with substantial change in its temperature, then it will be very difficult to match the temperature coefficient of all these registers, because you know that resistance of a resistor changes with temperature, and it will be very difficult to get so many resistors with identical value of the temperature coefficient of resistivity, and therefore, they may lead to erroneous results, particularly at higher temperatures. Then we require low switch impedance, can be expensive at higher resolution just because of the precision related issue with lower resistors. And also when we are dealing with a resistance very large resistance corresponding to LSB, like just the situation we are talking about, there this resistance itself may be somewhat similar to or maybe even larger than the input resistance of the amplifier itself, and therefore, that will lead to significant amount of error in the final result. So, as long as we are dealing with low number of bits, then it is fine. It is an excellent kind of converter, it is quite accurate, give very fast conversion. However, as the number of bits keeps on increasing, it becomes quite difficult to handle. Let us solve one problem on this. Here we are, our problem corresponds to an 8-bit DAC, just shown here. This is the least significant bit having register R0, this is the most significant one having register R. So, it is R, next one will be having 2R, this way the least significant bit is having 2 to the power 7 times of R. Here it is given that this VR, the reference voltage, is equal to 5 volt, then what is the smallest value of R that we can allow, which will provide you which can limit the current drawn from the source to 10 milliampere. This is a fabrication related problem, that is, it is said to the manufacturer that we have to limit the current to 10 milliampere, the maximum current that may appear in the system, and so accordingly he has to choose the value of these resistors. Now, how can he proceed? The maximum value of the resistor how can he select this? This is an 8-bit DAC. So, what is the maximum binary input that it can have? The maximum will be the one when all the 8 bits are having 1 in it. So, this is the largest possible input that it can have. So, how much is the current corresponding to this? The current corresponding to this will be VR divided by R into 1 plus 1 by 2 plus 1 by 2 square plus dot plus 1 by 2 to the power 6 plus 1 by 2 to the power 7, where R by 2 to the power 7 R is the register for this least significant bit. Or if we take, just for ease of calculation, if we take 2 to the power 7 out of this, then we have 2 to the power 7 plus 2 to the power 6 plus 2 and 2 to the power 0, that is 1 here. So, how much should be the value of this? This is just like a geometric progression, is not it, where the starting value of the smallest value is 1 and they are having a ratio of 2, the neighboring values. So, if we calculate properly, then this comes VR by 2 to the power 7 R, and this entire thing will be coming to the 2 to the power 8 minus 1 by 2 minus 1. So, like this, and so we have 2 to the power 8 is 256 minus 1. So, it is 255 by 2 to the power 7 is 128 into VR by R. So, that is the expression for the current when all the bits are switched on. Now, in this problem it is given that this I is equal to 10 milliampere in the extreme situation, that is 10 into 10 to the power minus 3 ampere. So, if we rewrite this expression, then the R, the smallest value of R mean, I should say this was I max. So, R mean should be 255 by 128 into VR divided by I max. So, we put the numbers here, 255 by 128 into your VR is given as 5 volt and I max is given as 10 into 10 to the power minus 3. So, we have to calculate the value, and I actually have pre-calculated the number. So, it is coming as 996.09 ohm. So, this is the smallest value of resistance that we can put in. Practically we would always like to put in a resistance value higher than this. So, this way we can do calculations about the design parameters, how to decide the value of resistor or even how to decide the value of the voltage. Let us extend this problem a bit. Next problem is, if RF is equal to R, what is the resolution of this DAC? This particular RF is given to be equal to R. Now, we have to calculate the resolution of this DAC. How can we calculate the resolution? What the resolution refers to? The resolution refers to the change in the final output with the smallest possible change in the input. Now, what can be the smallest possible change? Think about what is the smallest possible input, or rather I should say what is the smallest value of output you can get, that is 0, and it should correspond to which input? It should correspond to the input of all zeros. So, this is going to give you an output of 0 volt. Now, if we change this by the smallest possible amount, that is change by 1, then how much is the change that is going to take place? That should give you a resolution. So, let us calculate the output voltage corresponding to this. Your output voltage in that case will be equal to VR into RF upon R into all this resistance. Now, here all are 0, only one that is appearing, or if we expand 0, 0 by 2, 0 by 4, this way it continues, 0 by 2 to the power 6 plus only one appearing is the least significant bit. So, RF is R, that means your value that is available with you is equal to VR is 5 divided by 2 to the power 7. Actually, I lost where I wrote down the value. So, it is coming to be 0391 volt. So, this is the resolution. That means, each of the division it is 8 bit DAC. So, 8 bit means total 256 levels it can have, and each of the level corresponds to a voltage difference of 0.0391 volt, which is sufficiently small resolution, and as 8 bit suggests, it is a quite good converter. If we can extend this problem to identify the maximum output voltage that we can have. Now, when we can have the maximum output voltage, minimum output voltage is all inputs are 1, then sorry, all inputs are 0. So, we shall be getting 0 output voltage. Then maximum output voltage you are going to get when all inputs are 1, just like this. So, what will be the value of the corresponding output voltage? We actually know the value of the R by now, but the value of R is not required. The maximum output voltage, which is the maximum that you want to calculate when all of them are set to 1. So, that will be equal to VR into RF by R into all set to 1, 1 plus 1 by 2 plus 1 by 4 plus 1 by 2 to the power 7. So, again if we calculate following the same way and putting RF equal to R, then we are going to get this to be VR divided by 2 to the power 7 into, inside this bracket it is 2 to the power 8 minus 1, that is 255 by 128 into VR, and we know the value of VR is equal to 5 volt. So, 255 by 128 into 5, that gives us 9.9609 volt. This is the maximum output voltage that that will correspond to when all inputs are set to 1. I have one final calculation here. What will be the output voltage for digital input of this particular one? Now, following the same way you can calculate. Let us just calculate following the same pattern. Here your output voltage will be again VR into RF by R into, let us put the resistor. So, first bit B for the most significant bit, this is equal to 1, then it is 0 by 2, then it is 1 by 2 square, then again 0 by 2 cube plus 1 by 2 to the power 4 plus 1 by 2 to the power 5, 0 by 2 to the power 6 plus 1 by 2 to the power 7. And once you put all these numbers, then you are going to get 6.7578 volt as the final answer. So, corresponding to any digital input within this 8 bit range, you can calculate the output voltage just following this sample calculation. So, this is a quite good example about how to deal with a binary weighted register network or ladder network for conversion of a digital input to corresponding binary output. I hope you have understood this. Similar problems will be given in the assignments also, and I am sure you will be able to solve it. But let us quickly check the other kind of converter that we can have. As you have mentioned, there are so many number of resistors available here. So, it quite often may become difficult to deal with, particularly when we are having large bit, or we are trying to talk about a high resolution converter. Like this is this particular example corresponds to 8 bit, and that is more or less the practical limit of operation for such resistors. We hardly will find a binary weighted resistor of 10 or 12 bit. So, the next one that we have is called R2R ladder network. So, in this case, here each of your bits, here your switching setup is quite similar, but we have an additional resistor for each bit. Like if you see, each of these bits, this is the most significant bit, this is connected with a resistor of 2R. So, all bit pass through this resistance of 2R, and then in between these two connection there is this resistor R, this additional resistor. Similarly, if you focus to any one of them, like if we check about this particular bit, this is the resistor 2R, and either side of this connection you have this R resistor. So, the least significant the bit, more resistor the signal has to pass through, because like when you are talking about the most significant bit, it will only, while going through the comparator, it will only go through this, means it encounters only this resistance this 2R and another 2R. Whereas, if we come to the least significant bit, that will pass through this 2R and then this entire series of R networks or R register it has to pass through. So, the lower the significance of the bit, more number of register the signal has to pass through to reach the comparator. Here current is divided by a factor of 2 at each node following the Thevenin's theorem. Accordingly, we get this particular expression of the voltage output, which we can combine. Here this in the previous case of binary weighted register, here we had b n minus 1 by 2 to the power 0 and this one was 2 to the power n minus 1. However, there is an additional 2 factor is coming in the denominator here, giving this the final expression where we have an additional 2 in the denominator. But how we got this expression, probably it will be easier if we discuss with a smaller example. Let us take this circuit where we have just 4 bits. This is the most significant one, this is the least significant one. So, we have to keep on reducing the circuit to smaller case. This circuit can be thought to be equivalent to this, where all this S0, S1, S2 and S3 refers to the value of the concerned bit, like S0 refers to the value 0 or 1 which occupies the least significant bit. Similarly, S3 corresponds to the most significant one, and we have to we can reduce this circuit to a much lesser one to calculate the final output resistance value. Like if we think about this way, all the inputs are 0. Let us say all these S values are 0, then this is perfectly grounded, each of them. Let us take first this portion. There you can clearly see there are 2 values of 2R resistors in parallel. Then what is the corresponding equivalent resistor? Corresponding equivalent resistor will be R only, because you know their equivalent resistance, the equivalence of this 2R resistor will be 2R into 2R divided by 2R plus 2R. So, that leaves you 2R divided by 2, that is equal to R. So, this is this R that we are getting, and this is following Thevenin's theorem. Now, we can reduce it further. So, if we now think about this particular block, in this block what we have? We have one R here, another R here, 2 R resistor in series, another 2 R resistor in parallel. So, if we reduce this, this again will reduce to another R resistor like this. Now, we take this part, again we have one R, another R resistor in series. So, the net of these two is 2R and that is another 2R in parallel. So, combining them we get R. Finally, what is the equivalent resistance of this? So, R plus R in series 2R and parallel to this is 2R. So, another R. We have this entire circuit comes to be or comes to have an equivalent resistance of R only. This is the biggest advantage of this R2R ladder network, means whatever may be the number of bits that you are dealing with, the output resistance is always equal to R. We are using just 2 resistor levels, R and 2R, and they are oriented such that their combination gives you a net output voltage of net output resistance only of R. Let us take the example. An example where your S0 or B0, let us stick to our notation of B0. So, your B0 is equal to 1, all other base, that is B1, B2 and B3, they all are set to 0. So, the situation is somewhat like this, these all are grounded, and but this one is having this VR, the reference resistor. This can be, now we can reduce this, say we take this particular portion, there are 2 2R resistors. So, if we combine them, their equivalent becomes R and this voltage gets divided by VR by 2. Now, we take this particular circuit, we reduce that, the voltage becomes VR by 4 and the equivalent resistance is R. Now, we take this particular circuit, this is just simple application of the Thevenin's theorem and circuit theory. So, again it becomes VR by 8. In each step the voltage gets divided by 2, by a factor of 2. Whenever we are moving from one node to the next one, the voltage keeps getting divided by a factor of 2, and in all cases the equivalent resistor is coming to be R. Like here also the voltage is VR by 8, resistor is R. Now, this is the only circuit that is left with us. So, again the equivalent resistor will become R and the voltage will become VR by 16. So, corresponding Thevenin voltage we are getting as VR by 16. That means, when you are dealing with an input of 0 0 0 1, it is like this, or instead of writing this, so you can think about any one appearing the least significant bit will contribute VR by 16 amount of voltage. Similarly, if we set say B1 equal to 1 and everything else to be 0, then this circuit does not come into picture, and actually you will be having this VR voltage appearing here. So, if we calculate that, its contribution will be it is like here it passed through, the voltage passed through 4 nodes. So, we got VR by 2 to the power 4, or we write it as VR by 2 to the power 4, but here it will be VR by 2 cube. Similarly, when we have B2 equal to 1 and others are set to 0, then that will contribute VR by 2 square, and when the most significant bit is set to 1, everything else to 0, then that will contribute VR by 2 to the power 1. That means or that way we can calculate the voltage contributed by each of the bits. And now depending on which of the bits are available and which are not, we can always keep on adding them or subtracting, we can always keep on adding them to get the final output voltage. So, like when we have an input say 0 1 1 0, then what will be your voltage? Then the most significant bit is not there, the next one is 1. So, the B2 is 1, so it will contribute VR by 2 square, B3 is 1, that will contribute VR by 2 cube, least significant is 0, so that will not contribute anything. So, this way we can get the final output voltage, and this is the expression. So, B3 contributes B3 by 2, B2 contributes B2 by 4, B1 by 8, and least significant contributes B0 by 16, and now multiplying with the RF, we get the final output voltage from this. This is an example of dealing with, here we are dealing with talking about a 2 bit resistor. This is the least significant bit, this is the most significant bit, and your input digital input is 101, that is the both most significant and least significant bits are set to 1 and the intermediate one is 0. The reference voltage is 10 volt, your R is given to be 2 ohm and RF is set to be 2 R. Then how can we calculate the value of this current first? So, we have to calculate the final output voltage. Let us calculate the output current first. Your I naught, the current, will be equal to minus of this V ref divided by the equivalent resistance. How much is the equivalent resistance? We have this 2R associated with this in series, and this 2R is in parallel to that. So, 2R parallel 2R. So, that means we have minus V ref divided by 3R. Now, V ref is said to be 10 volt divided by 3 into 2 is 6. So, minus 1.67 milliampere, or I should say not milliampere, 1.67 ampere. So, how much is the current that is coming to this op amp? That current I naught reaching the op amp then can be written as this I naught into the contribution coming from the most significant bit is 1 by 2, from the next one is 0 by 2 or 0 by 2 square, and from the least significant bit is 1 by 2 cube, that is I naught into half plus 1 by 8. So, 5 by 8 in times the I naught. So, 5 by 8 times 1.67 minus 1.04 ampere. Then final output voltage will be I naught of this op amp into RF, that is 1.04 minus of that into RF is how much? 2R into 2. So, that is something like 4.17 volt. So, this way we can calculate the output voltage that we are getting from this resistor network. It is a much more complicated structure compared to the binary weighted resistor circuit that we have discussed, but it has much bigger advantages once we have control over this. The biggest advantage is there are only two resistor values to consider, R and 2R, whereas in case of the binary weighted resistor we have to consider a very large range of resistance to deal with. Actual value of R is of less importance unless very high values are employed here, easy to manufacture or implement. However, it is much smaller speed compared to the binary weighted value, which is having some kind of parallel processing, and so very quick to give the final output and much complicated to analyze this particular system. You need to have proper idea about circuit theory to do this, but still because of such simplified final representation only and requirement of only 2 resistance values. So, this is probably more popular one when you are looking for very precise measurement, and particularly when you are looking for larger bit of measurement, larger resolution. However, when you are looking for somewhat restricted resolution up to 6 bit or 8 bit, then the binary weighted one is more preferred, simply because of its simplicity. That takes us to the end of our week number 3. Here we have talked about the application of digital techniques in measurement. So, we started with defining the significance of digital analysis, storage and transmission over corresponding analog counterpart. Then we talked about the number systems, conversion from one system to the other, particularly conversion from decimal to others and from other system to decimal, and from there we established why binary is so important compared to the other systems. Then we talked about the binary logic gates, their combinations to give different kind of conversion of binary digits. Then we talked about the decimal to BCD and gray encoders. We have talked about alphanumeric codes in detail, particularly the ASCII character sets, the Unicode systems, and also a bit on the barcodes. Then we have talked about the analog to digital converters, out of which successive approximation and flash ADCs are generally the most popular one from modern technology point of view, but sigma delta it is quite complicated, but can be much more accurate. And today we have discussed about this digital to analog converters, where we have discussed only 2 configurations, the binary weighted one and also the R2R ladder networks. So, please revise all these lectures properly. If you have any query, please write to me. I would request you to refer to books or maybe over internet, because you will get lots of different kinds of discussions regarding each of these topics. This course being focused more on mechanical measurement, so intricate details of electronics is not required, but at least the topics such as the number systems, how to combine the logic gates, what are the working principles of each of these converters, if you have understood that, that is sufficient. So, that takes me to the end of this particular week. It was actually a quite exciting week for me, because we talked about something which is quite out of scope for a mechanical engineer. But being as we are living in a digital world, I felt it is extremely important to have some idea about how to convert a normal analog input to digital and how to get it back to the analog form, and that is why we have discussed in detail in this week. I hope you have enjoyed it. Please do the assignments again, and I repeat, if you have any query, please write to us immediately. So, I will try to be sorting that out as soon as possible. So, next week we shall be talking about the processing of the outputs. So, till then, bye. I am signing off for this week. So, take care.